So every mass in the universe attracts every other mass. How big is that interaction? Well, Newton came up with the law. This is the law. How much you attract to other masses, okay, so you have to factor in your mass, the mass of the other mass, so both masses go in there. The R in the denominator is their separation. And it's really important to measure that separation center to center. Newton struggled with that for a while. Why should it be center to center? And in order to figure out why it should be center to center, what he did was he took each of these objects, let's say they're spheres or something like that, he chopped them up into tiny little bits and measured the attraction force between every pair of objects, and found that if you laboriously figure out every single bit attracting every other bit, it's equivalent to taking the entire masses and taking their center-to-center separation. So it's a big shortcut. In order to prove that, he had to come up with the math that it takes to chop things up into little bits, figure out contributions, and then put them all back together again. That is called calculus. It wasn't invented at the time, so he invented that too. Okay? So this was one of the original problems that calculus was applied to. Okay? So we can just take benefit of this shortcut, not worry about anything else, take the entire masses and measure them center to center, and we're good to go. Now, let me point out that the force of gravity is proportional to 1 over r squared. This relationship comes up so much in physics, it gets its own name. It's called an inverse square law. Inverse square law. So it's when the force is dependent on the inverse, meaning denominator, square, meaning squared, of the distance, or separation distance. Okay? So this is why I tried to drill in proportionalities from the very beginning, so you can tell me stuff like, if you triple the distance between the masses, what will happen to the force of gravity? If nothing else changes, the force will be what of its previous one? 1/9, right? Stuff like that. So the force gets weaker with distance, and proportionalities can tell us exactly by what factor it gets weaker. All right? The final ingredient, this, capital G. Capital G is called the universal gravitational constant. It is the constant which determines something about the strength of the gravitational interaction everywhere in our observable universe. Now, it really makes sense that the factor is there, because otherwise it would be a freaky coincidence for it to not be there. Because if you take a 1 kilogram mass and a 1 kilogram mass and put them 1 meter apart, it's not going to lead to 1 Newton of attraction. Those are all arbitrarily picked things, right? 1 kilogram is arbitrary, picked by somebody. 1 meter is arbitrary, picked by somebody, right? So that would be a weird coincidence. So that multiplier is just there to make sure that everything works out properly. How do you measure it? Well, you do basically that experiment. You put a 1 kilogram mass and a 1 kilogram mass. You put them 1 meter apart. And then you actually experimentally measure the force of attraction. This was done at first by someone called Cavendish. And as you can imagine, it's a very careful experiment, because the force of attraction is not going to be 1 Newton. It's very, very tiny. Okay? You probably never left 2 1 kilogram masses on a table 1 meter apart and come back later and they've gone together. Okay? The force of attraction is very minute. The static friction force can easily cancel it, and even then it would take a long, long time for them to come together. The amount of attractional force that they would have is 6.67 times 10 to the minus 11th newtons. Okay? I think that's right. Looks funny. Pretty sure. So it's a very minute force, okay? And if you flip this equation around, of course, this lets us identify experimentally what is the universal gravitational constant, and that value, if you, this is an experiment, okay? That's 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Ugly batch of units on there, yes, but necessary to make the equation work out. So this force is very small, okay? You've probably never seen two objects that you left on the table kind of get sucked together while you were out of the room or before your eyes. You probably never walked down the street with your friend. You suddenly get pulled together because of the force of gravity. The force is very weak, okay? This universal gravitational constant tends to make this force very weak. So it seems like it kind of deflates the initially kind of amazing claim that every mass in the universe attracts every other mass. But even if we have two masses that are relatively decently sized and relatively close together, the force is so minute as to not even perhaps warrant mention. So the next question is, if every mass in the universe attracts every other mass, then when is this force ever going to amount to much? Question? No?
Kind of.
Yeah.
This might be kind of where you're going, but if you were to have like 2-kilogram objects in like a frictionless vacuum, like would they ever come together? Or is it
they would eventually go together, yes.
How many like years?
A long, long time. In fact, that's why most of the universe in the early days was not much of anything. It took gravity a long, long time to pull the hydrogen in together and start to initiate stars, right? Stellar fusion, right? So it takes a long, long time for gravity to bring things together, even if you're in a frictionless vacuum, which on Earth we pretty much never are, right?
So are we talking like thousands of years or like millions of years? Or like
the
millions?
Earth is definitely more than 6,000 years old, okay? So.
But I mean for like this to ever, for us to ever see that happen.
Yes, it takes millions of years. Okay, so so this is, let me go over here. So our next most sensible question is, when is the force of gravity ever sizable? So how do we get out from underneath the fact that we always have this incredibly tiny number multiplying through, okay? And by the way, I should mention Cavendish was the first person to do this, but this, with current technology, you can do this as an upper division undergraduate. So this is, we run this over, you know, in Thornton Hall. One interesting kind of thing about science, you can plot the measurements of G versus time. So Cavendish got it here, then the next person did it, got it about here, then the next person did it, got it about here, and then it kind of leveled off. So what does that tell you? It tells you the first people weren't brave enough to go out on a limb and say Cavendish was that far off. So they said, it's a little more than that. The next person said, yeah, it's a little more than that, and they finally figured out Cavendish maybe was a little low, and everyone kind of eventually settled on the right value. Okay? It's very hard to do. It's very hard to measure the minute attraction between two different masses. And you know, if someone walks by in the next room, that can be enough of a confounding error, because that's a mass passing by in the system, right? So when is the force of gravity sizable? How do we get it so that it's not this tiny little minute force that is very hard to measure? Well, you need something in the formula to offset the tiny number in the front. Well, one or more masses or one or both masses must be very large. That's one thing you can do, because of course what you have is if you have a tiny number times gigantic number, then tiny times gigantic might work out to be something decent, right? So, what would be a very gigantic mass? How about the entire Earth, this big rock we live on, okay? So the Earth does not have any special properties where it can pull gravitationally on you and other things can't. It just happens to be big enough so that you notice, okay? So while you are attracted to every single mass in the universe, the big one that you notice is the Earth, okay? The Earth has no special powers. This is a club that all masses belong to. Question?
Does the fact that Earth is moving have an effect on that gravity?
Nope, it has no effect on the gravity. It can have an effect on your apparent weight, but it has no effect on the actual pull. That's just, there's no factor in this for motion, right? It's just the mass is in how close they are. So the second point, okay, what about the sun? The sun is 1,000,000 times more massive than the Earth. Why don't I get just plucked off the face of the Earth and pulled into my fiery death in the sun? It's the distance too, right? So you have to, one or both of the masses must be very large, and they have to not be too far apart. Because as r increases, the force of gravity will decrease. So they cannot be too far apart. So there's only one object usually that passes through both of these sieves. You have a very large mass that's very close to you. What is it? Okay, it's the Earth. So that's the one force of gravity that you notice, even though every single mass in the universe has an attraction to you as well. Okay? So I have a gravitational attraction to this pen. I have a gravitational attraction to the Earth, but the Earth is the one that I notice. Okay? Okay? So let's go ahead and apply this equation to the Earth system. So the mass of the Earth and me on it. Let's see what we get. Well, if I'm going to put all the equations into the all the variables into the equation, I have to put the mass of the Earth, the mass of me, and then what do I put in the denominator? Do I put in 0 because I'm standing around on the Earth? No, remember you have to do it center to center. Which basically neglecting the fact that I'm not nearly as big. Basically, that's the radius of the Earth, right? All right. Now, if we were all going to do this, the only difference between me doing this and you doing this is that your little m would be different, right? So it might be nice to prepackage this stuff, and then we can all multiply in our own masses, right? So we go ahead and plug in. The mass of our planet is 5.97 times 10 to the 24th kg. Don't need to memorize that. You have it now in your notes, and it is available on the equation sheet. I'll talk about how the heck do we know that in a second. The radius of the Earth, 6.38 times 10 to the 6 meters. I'll talk about how do we know that in just a second. And then, of course, the third ingredient is that universal gravitational constant that Cavendish first measured for us. And if you plug in all that and figure out the number and figure out the units, you get 9.8 meters per second squared. So It's no wonder. We've been packaging up all that other stuff as g, little g. Okay? So now we know, where does our value come from? Where does g come from at the surface of Earth? This is where it comes from. It's the universal gravitational constant coupled with some particular parameters of our planet that we happen to live on. So let's go over here. We can start checking off all the things that we were previously just had to be told. We can go back and figure out why. Why does it have to be the Earth? Definitely needs to be the Earth. Earth variables abound. Okay? Mass of the Earth, radius of the Earth. You have to be near the surface because the center-to-center distance has to be approximately that. Otherwise, it can change. So we know that now. Why is it downward? Well, gravity is attractive. Masses attract. You get pulled down because the Earth gets pulled up because you're attracted to each other. Why is the value this? We just showed that. Okay? And then finally, how is it that all objects get given this acceleration? How is it that gravity knows to pull harder on things when they need it? When things have more mass, gravity pulls on them. Well, mass is your entry into the gravity club too, right? So if you have more mass, yes, you need more force, but you automatically get more force, right? If you have more mass, you will be pulled towards something harder, and it's pulled towards something just harder so that you have the same acceleration as everybody else. Now that in itself is kind of an amazing thing. I should point out that the m in F net equals ma, that is inertia, right? That is the resistance to motion from any type of force. That we call inertial mass. It's how stubborn you are to change. This we call gravitational mass, which is your entry into attracting other masses. And so far as we can tell, those don't have to be the same, but they are the same. So the kind of inertia the property which measures your resistance to all acceleration, regardless of the force, that's exactly the same thing as what gains you entry into the gravitational club. And that is what causes your acceleration to be independent of your mass. It suggests that there's something truly fundamental about the force of gravity. It uses the same exact idea of inertial mass, and that is also your entry into the gravitational club. This is where you can go down the rabbit hole to Einstein's theory of general relativity, which assumes that your inertial mass and your gravitational mass are the same thing. Okay? It just suggests something truly fundamental about gravity, that it can make everything accelerate exactly the same, because the amount of pull that you get is always going to be such that it makes everything accelerate the same. So we've now solved why is everything given a constant acceleration by gravity. It's because more mass means you get pulled harder. That's the nature of gravity. Okay? So we've now, with this law, seen how all of the features of gravity that we already knew about just fall right out. I'll say a few brief more words here. First of all, how do you get the radius of a planet? Well, this was done in BC times. The idea of the world being flat, that's people thinking that for a long time, that's way overblown, okay? If you had countries where they lived on the ocean, they could see the ships sailing away and the mast being the last thing to disappear over the horizon. People knew the Earth is curved. How do you figure out its exact size? It's just a matter of geometry. First person to do this was a guy named Eratosthenes. He did it in BC times. It's just a matter of simple geometry. Here's how you do it. You have sunlight coming down toward the Earth. Basically plant a stick. When the sun is overhead, it casts no shadow. But somewhere else is casting a shadow. So you can measure these angles, figure out what is the angle difference. The hardest part for him was figuring out how far apart they are on the Earth's surface. And of course, if you know this much distance covers this much angle, you just extrapolate to how much distance it would take to make a full circle. So that was a relatively straightforward thing to find the radius of the Earth. Now, how do you find the mass of the Earth? That's a much harder thing. And here's where I kind of tell you something. Cavendish wasn't really interested in the universal gravitational constant for the purposes that we would think of it today. Here's why he was interested in it. You guys measured this in your lab, right? You drop things. Eratosthenes supplies us this. The reason why Cavendish wanted G is because what he was gunning for was the mass of the Earth. That was his main interest. The universal gravitational constant was like, yeah, okay, I want that, but what I really want to do is find the mass of our planet. Why did he want to find the mass of our planet? Well, mass over volume is density, and then people had no idea what the Earth is made out of, but maybe the density would give some kind of clue. Okay? So Cavendish's legacy is being the first person to measure this universal gravitational constant, but he wasn't really going for that at all. Okay? Now you might say, well, how do we know any of this stuff is right? Right? Maybe the mass of the Earth isn't really that, and the gravitational constant isn't really that either. Maybe they just multiply to that value. Well, of course, this is science, right? You triangulate with lots of other observations, and you come out with the conclusion that they were correct. Okay. All right, so we'll come back to this next time. Let's knock off for today.